So the majority of these problems here primarily deal with the MC delta T equation. And we're going to start out with some fairly simple situations and then work our way to more complicated situations. So our first question here, we say we have a sample of nickel and we have its mass, and we're told that it changes temperatures. And we're told how much heat, how much energy it took to do that. And so what we have to figure out is what is the actual specific heat. So we recall Q equals mc delta T. Well, Q we know in this case, that's the energy, 975 joules. The mass is given is 425 grams. What's the specific heat capacity? Well, that we don't know. That's what we're trying to solve for. And delta T is just the difference in temperature between 31.55 and 26.2, which is 5.35 degrees Celsius. So we can just solve this equation for C, and we get our specific heat capacity for nickel is 0.429 joules per gram per degree Celsius. Question 2, we have the exact same situation. Again, we're trying to solve for the heat capacity of, in this case, zinc, but again, for the metal. So we set it up the same way. The amount of energy or heat is equal to the mass times C times the change in temperature. Again, we can solve for C and we get 0.386 joules per gram per degree Celsius. And then in part C, now we have the amount of energy, the mass, and the heat capacity. We also have the initial temperature. What we're trying to figure out is how much that will change the temperature of the copper. So in other words, our unknown here is delta T. So Q is 150 joules, is equal to the mass, 75 grams, times C, given as 0.38 joules per gram per degree Celsius, times delta T. If we solve this for delta T, we find that the change in temperature is 5.3 degrees Celsius. But we're not quite done at this point, because we're not looking for delta T, we're looking for the final temperature. And so delta T is equal to T final minus T initial. And so T initial is what we're given in the question, 25 degrees Celsius. Delta T is what we just found. And so if we solve that, we get that T final is 30.3 degrees Celsius. So for the most part for this course, these are the types of problems I'd like you to be able to do. Now, the last two problems are a little bit more challenging and certainly worth giving a try too, but these are a bit harder. So in question 4, what we're saying is that we mixed two solutions of water, or two samples of water. One of them is at 75 degrees, one of them is at 15 degrees. And we want to know what's going to happen to the temperature here. What will the final temperature of this be? When we mix these two. And we can't just say it's going to be the average of the two because we don't have equal amounts of water. If we had equal amounts of water, then we could, yes, assume that we would end up right in the middle. But there's a very important hint in this question, and that's where it says that the heat gained by the cold water is equal to the heat lost by the warm water. So I'm not sure why that did that. Let's start again. So we can calculate a Q for the cold water. We can also calculate a Q for the hot water. But based on that assumption that we made, the hint, the heat given off by the cold water is equal to the heat lost by the warm water. The only difference here is that because one of these is gaining heat and one of them is losing heat, the signs will be opposite. So we can say the Q of the cold water is equal to the negative Q of the hot water. So that means we can say mass of cold water times C of cold water times delta T of cold water is equal to the mass of the hot water times C for the hot water times delta T for the hot water. But immediately I can simplify this. And how can I do that? Well, in this case, I know that these are both water. And because they're both liquid water, the heat capacity for both of them is 4.184 joules per gram per degree Celsius. So what does that mean I can do? I can do that. Now I've got a much simpler equation to deal with. And we don't want to forget our negative sign here. So now we can say the mass of the cold water, which is 15 grams, times delta T of the cold water. So the final temperature of the cold water we don't know. What's the initial temperature of the cold water? That's what's given in the question as 15 degrees Celsius. That's equal to the mass of the hot water, 75 grams. Again, let's get our negative sign in. Times the temperature, the final temperature of the hot water, which we don't know, minus the initial temperature of the hot water. Now notice I'm not differentiating between the final temperature of the cold water and the final temperature of the hot water. Why not? Well, if we're mixing these together, then that temperature should be the same. All right, so let's work through this. On the left side, 15 T final minus 225 is equal to 75 T final minus 75, or well, since they're both negative, plus 75 times 75. Which is 5,625. Now I'm just going to rearrange so that like terms end up on the same sides. We get 90 T final is equal to 5,850, and if we solve for T final, we get 57 degrees Celsius. So this is an answer that makes sense because it's in between the two starting temperatures, 15 and 75. But in addition to that, since we had more of the hot water, this final temperature is closer to the hot water than it is to the cold water. All right, our last problem, we're taking some metal that's been heated up and we're adding it to a sample of water that's right around room temperature. Now, what this situation is if we were trying to calculate the heat capacity of an unknown substance or even a known substance, this is how we might do something like that. So we'd look at the mass of the metal times the specific heat of the metal times delta T of the metal. And this is equal to the mass of the water times C for the water times delta T for the water. And now we can start filling in the terms that we have. So the mass of the metal is given in the problem as 72 grams. The C for the metal is unknown. That's what we're solving for. And delta T for the metal is the T final, 29.1 degrees Celsius, minus T initial, 97 degrees Celsius. We can set this equal to the mass of the water, which is 100 grams, times the heat capacity of the water, times the delta T for the water, which again, T final, which is 29, minus T initial, which is 25, gives us 4.1. From here, this is just basically algebra, and we solve the C for the metal is 0.351 joules per gram per degree Celsius.